Before I start off today's video, I just want to quickly say that I now have a Twitter account. I go by as C_YT on there, so feel free to follow me to get updates on when new videos go live, as well as other random life updates that are going on. You can also help the channel grow by simply subscribing if you enjoy this content. Anyways, enough of all that, let's get on with the video. Hello everyone, and welcome back to the C-Squared channel. Have you ever wondered if it was possible to walk through a wall, like perhaps how a ghost would? Well, according to quantum mechanics, the study of the very small, that could very well be a possibility. Now upon hearing that, don't go ahead and immediately ram yourself into a wall hoping you can make it through. Oh no, I would advise strongly against that for your sanity and physical health. It may be possible, yes, but the chances of this happening are extremely slim, essentially almost zero, at such massive scales like us humans. But why is there still a chance? It's all because of something known as quantum tunneling, a mysterious phenomenon that arises from working with quantum mechanics. When measurements get so small, things get to a point where you can't really get any more precise with what you measure. This limit of precision is known as the Heisenberg uncertainty principle, which governs quite a lot of quantum phenomena. The principle limits the precision of measuring properties of quantum scale particles. These usually come in two pairs. You have energy and time, and you also have position and momentum. What this means in practice is that you could find the precise energy of a particle, but you want to be able to find the time at which the particle had this energy. You could also find the exact position of a particle, but you wouldn't be able to obtain its momentum, which is how fast it is moving. The same goes in reverse, so you can find the time at which you can detect a particle, but you can't really pinpoint its energy at this time. You can also find the momentum of the particle, but you would not be able to get a precise location of it as it moves. Due to this, we have to predict some values, which lead into a ton of probabilities being thrown around. So how does this relate to today's video? Well, because quantum mechanics is probabilistic in nature, we can never be so sure as to what can happen with particles, as we get some really bizarre events happening. Let's set up a situation here. Assume we have a single electron sitting on a flat horizontal plane. At this point, the electron has no outside energy, and so it can only move left or right while sitting on the plane. We call this the ground state, which is the minimum energy a particle can be in. If the electron begins to move up, then it has acquired some extra energy, with energy being represented by this axis here. If the electron moves down, then it has lost energy. Now we're going to introduce an obstacle. We're going to place the electron to the left of the central point of this graph and give it some energy E. Now a barrier will be placed just to the right of the central point with a width of D, and we'll give this an energy of V. And this is ensured such that this will always be higher than the electron's energy. So in such a case like this, the barrier we're talking about could be a line of particles that could push the electron away, or it could be some kind of force field, for example a magnetic or an electric field, which can also repel the electron away. We now arrive at this scenario. What's going on here? Well, the electron is currently chilling on the left side of the graph, and it can freely travel anywhere on the left side and up until the central point, until it reaches the obstacle. Because the energy of the electron is less than the height of the barrier, it cannot pass through the barrier. Therefore, in order for the electron to cross the barrier and make it further into the right side of the graph, it needs to gain enough energy to jump over the barrier. So the energy of the electron needs to be greater than the height of the barrier. In a classical setting, if the electron does not have enough energy to overcome the barrier, then it will never be able to pass through to the other side, and instead it will just bounce back, like a ball being thrown against a wall. However, we're not talking about classical physics here, since we're down to subatomic scales with electrons. We need to look at the quantum behavior of this interaction instead. Unfortunately, things are not so simple because of the uncertainty principle, so we don't know for sure where the electron could be at any moment in time, as well as its exact energy. This crucial principle therefore gives us a very strange event that could happen. Let's look back at the same situation as earlier. The electron is on the left side of the graph and the barrier is to the right. The electron's energy is less than the height of the barrier. Because of the uncertainty principle though, we don't exactly know where the electron could be as it moves, and we also don't know exactly the energy of the electron at any point in time. And so there's actually a random chance that the electron can spontaneously appear on the right side of the barrier, despite appearing to have less energy than is needed to jump across. So, essentially, it just suddenly tunneled through, and that is what we have known here as quantum tunneling. At atomic and subatomic scales, like what we have here with the electron, quantum tunneling is actually quite a common occurrence. Using a simple model I created, I came to a conclusion that electrons generally have roughly a 50% chance of tunneling across a small barrier. Now on my second channel, C Cubed, I'll be making some extra content from this video explaining the model itself, and a somewhat complete derivation for it for those who are interested in seeing the maths and calculations on how I arrived at this conclusion. But anyway, what this 50% chance means is that half the time you can expect incoming electrons to suddenly appear on the other side of the barrier, despite them all having less energy than is needed to jump in. Such a bizarre phenomenon has been made quite useful in recent times thanks to all sorts of developments in technology. One of the most impressive breakthroughs is in the world of microscopes. Thanks to quantum tunneling, we now have access to scanning tunneling microscopes, which utilize this phenomenon to scan a surface so precise to the point where you can actually see atoms. This is done by having electrons on the tip of a probe tunnel across a small gap towards these surface atoms. Depending on how you set up the microscope, and if you look at the energy difference between the gaps, you can generate some really impressive images, such as this mesmerizing image of a mostly clean gold surface. So now that we have some sort of understanding of quantum tunneling, let's go back to our initial situation once again. At the beginning of this video, I claimed that it could be possible to walk through a wall. Thanks to quantum tunneling, we're going to see why this is the case. So let's go back to our one electron situation, which is this graph here. We already said that sometimes the electron could suddenly cross the barrier without gaining any extra energy that would be needed to jump it. In this case, it was almost 50% of the time, but that was only because the barrier width for this situation was only 0.01 nanometers across, which is very typical for quantum situations. So the key thing to note here is that the probability of tunneling through a barrier decreases drastically when the barrier width increases. This can be explained mathematically with this relationship right here. In this situation here, we can see that T here is the transmission coefficient, which is basically the probability of an electron tunneling through a barrier, and D is the width of said barrier. What this means in practice is that if you increase the value of D, then the value of T will decrease exponentially, and that is graphed right here. So you can see how as you increase the value of the width D, you will see that the value for the transmission probability will continuously decrease. It also tends towards 0. So let's transform this situation into a large scale one. We're going to use the same electron and barrier from before, but we're now going to increase the width of the barrier dramatically. Since I'm in the United Kingdom, I'm going to use the thickness of an average house wall as width of barrier for the electron to tunnel through. So now, D is no longer 0.01 nanometers, but it is now 23 centimeters. we try to calculate the transmission coefficient T for this. I got this horrifying number. For those who can't comprehend a number like this, just know that this is basically a really, really small probability for this electron to successfully tunnel through the entire length of the barrier. So already this is actually extremely tiny. Now we're going to take this one step further. An average human body contains about this many atoms. For simplicity's sake, and to save my well-being from doing painful calculations, I'm going to regard all electrons in the human body as just electrons. In this case, the transmission coefficient now becomes this. Unlike the previous number, this one probably represents a decimal value that is several thousands of zeros before reaching your first actual number. It's so tiny that none of the calculators or sites I've tried can even compute such a thing. So when I say tiny, I mean tiny. This is the rough probability for your entire body to tunnel through a 23 centimeter thick wall. Essentially at this point, you basically just walked through a wall. Do note though, that this value is not accurate, since I made a lot of assumptions, and of course the model is not perfect. But ultimately I wanted to demonstrate the scale of such a probability like this, not so much the exact value. Now with such a tiny probability like this, if you continuously ram yourself against a wall all day every day, I predict it'll probably take much longer than the current age of the universe to even get a slight chance of tumbling through the wall. So I'd highly advise against trying. But do know that it is possible thanks to quantum mechanics. Although this happening is extremely slim and will never happen in our lifetimes, for sure. So thank you guys so much for watching this video. I hope you guys all learned something today. Be sure to subscribe to help the channel grow, and I'll see you all in the next one.